Okay, great. Okay, I'll go ahead and end the poll. Hopefully you can all see the results. So it looked like most people thought it was a great lab. A few people thought it was overwhelming, but most people thought it was on the better side of good. So that's great. That's good to know. I really appreciate that. Oh, that's what Eric was trying to let me know about. Thank you, Eric. Okay, so good. I'm glad you guys liked it. So let's just look at our schedule really quickly, and would love to here. I'll share my screen. All right. So hopefully you can all see my little browser window here. We just finished LMFRP. We're going to try to wrap up Haskell in the first half of this week, and then later this week we'll go ahead and move on, depending on how our Haskell lectures go, and we'll start our potpourri of various other lectures on various other languages. So we got the introduction to Haskell last time, kind of the cool idea that it's a lazy language, kind of a cool idea that as a result we can build recursive, lazy, infinite data structures, use them as part of calculation, and like not a problem. Haskell handles it just fine. So today, I'd like to just make one more point, a couple of points about laziness, why it's potentially a good thing, why it's potentially a bad thing, why we might like it, why we might not like it. And then, as we have time, we're going to try to move into functors, applicatives, and monads. So if you've never heard any of those words before, then we'll be learning a whole lot. Functors, applicatives, and monads are part of they're just some abstract concepts that Haskell is built around that gives it its powerful type system and lets us solve some interesting problems. Okay, but first I'd like to point out just a couple more things about laziness. So here's some Haskell code. I just found this on the internet. So hopefully you can all see that. Give me just a second here. Let me do this. I'm going to pin my video. Okay, so let's take a look at this Haskell code really quickly. So this is a quicksort function. And we've seen quicksort functions before in a couple of different languages. I think it's kind of fun to compare quicksort across different languages. So let's take a look at this quicksort function. Actually here, sorry, let me just apologize. Give me just a second. I'm just going to pull up our chat in case anybody has questions while we're doing this. Okay, so let's take a look at this quicksort function. So here's the type signature. And we'll talk about the type signature in just a minute. And here's sort of the rest of the function. So here's the base case. The quicksort of an empty list is just an empty list. Great. And notice it's Haskell, it's kind of like Elm, there's pattern matching. So if it's not an empty list, then here's a different, here's the second case. Second case is that you've handed us a list, and there's a head of that list, which is X, and there's the tail of the list, which is XS. Okay, so we've seen this before too. Here we see let smaller sorted be the quicksort of, and you give us a list. And what is that list? Well, this list is the list, we're using a list comprehension. So we're going to take A from the list of XS's, and we're going to put this little guard in that says that A has to be less than or equal to X, which was the head of the list. Similarly, we're going to create a bigger sorted list where we're going to quicksort, we're going to recursively call quicksort on what? We're going to call it on a list that we create with a list comprehension. What is that list comprehension? Well, we take all of the A's from the rest of the list and concatenate them together, join them together if they are greater than X. And then we're going to go ahead and construct the result, which is here. So we're going to take the smaller sorted list. Remember that plus plus is concatenate. We're going to concatenate that with a single element list, concatenate that with the bigger element list. Okay, so, I mean, this looks almost identical to like the prologue code that we saw when we were thinking about quicksort. But remember that Haskell is lazy. So here's a question that I want everyone to think about. And if you're like, really pay attention to this question for just a second. I wish I had a whiteboard or something, but let's imagine that I have a list of numbers and I call quicksort on that list. Haskell's lazy, which means it's not going to actually quicksort the list, right? It's lazy. It's going to wait until we actually need a result. So we could say sorted list equals quicksort of unsorted list. All right. Now, let's imagine that the sorted list is sorted from smallest to biggest. So let's suppose now that I take the minimum of the sorted list. Okay? And I print it out. So the minimum of the sorted list, by taking the minimum, what I mean is I just take the first element. The first element of the sorted list will be the minimum element in the list. And I print it out. So Haskell says, oh, you're going to print it out? Great. I need to actually compute the first element of the sorted list. And so it says, well, what is the sorted list? And it says, oh, well, the sorted list is the result of quicksort, which it hadn't computed yet because it's lazy. So here's the question. How much of the list gets sorted? I want you all to think about this. How much of the list gets sorted? Like actually sorted. So here's man, I wish I could like dynamically create a little poll. I mean, I sort of can, but it's actually kind of a pain. All right, hold on. I really want you guys to engage this really quickly, okay? I want you to think about this. So what I'm going to do is I'm going to quickly, this is just going to take a second, I'm sorry. I'm going to actually create a poll and we're going to see, I'm going to, because I want to poll you on this, okay? Sorry, I have to just rearrange my window here a little bit. Okay, we're going to add a new poll. How much of the list is sorted? Okay, I'm creating this little poll. I'm going to save the poll. I'm going to launch the poll. Hopefully we can see it. Okay, launching the poll. Tell me, how much of the list is sorted, right? So we've got a quick sorted list, which is lazily quick sorted. We're taking the minimum element, which is the first element of the quick sorted list. We're printing it out, so we know we need the first element of the list. But how much of the list actually gets sorted? Some of the elements, just a few of you are saying just one element. Some of you are saying all of the elements. Some are saying some of the elements. A few of you are saying it's not deterministic. Keep going. I'd love it if everyone would weigh in on this. What do you think about this? Okay, so looks like we've stabilized. So a few of you are saying just one element. So that's a majority vote. So let's think about this for just a second, because I think this is a really interesting question. How much of the list gets sorted? Let's look. So what we're going to do is we're going to think about accessing just the first element of the result of calling quicksort. Well, what's the result of calling quicksort? Let's imagine we're at the outermost layer of quicksort. We're going to call quicksort on some sort of list, And what does it return? It's going to return this. And we're going to take the first element of this. So what is the first element of this list? Well, we don't know what X is. So it's a little bit hard to compute, but let's just assume for the sake of argument, let's assume for the sake of argument that the pivots that we pick always happen to be in the middle of the list, all right? So what I mean is there will always be the same number of elements on the smaller side as there are on the bigger side, okay? Just for the sake of argument. So we're gonna take the first element of this whole list. Well, what's the first element of this whole list? First element of this whole list is the first element of smaller sorted. So right there, we see something interesting. Do we have to sort the right-hand side? Like, do we even know what bigger sorted is? Bigger sorted is it's like the right-hand side of the list. All we know is that these are things that were bigger than the pivot. But that's bigger sorted has been lazily computed as the result of calling quicksort. So all we know is that the things in bigger sorted are going to be greater than the pivot, but they haven't actually been sorted yet. And so this is like an unordered, it's not unordered, it's like it just hasn't been computed yet. But we don't need it. We don't need it to get the first element of this list. So Haskell isn't going to compute it. Okay, so right there we see that half of our list won't be sorted. It'll just be stuff that's bigger than the first half. Okay, now let's think about smaller sorted. Where does smaller sorted come from? We want the first element of smaller sorted. Well, smaller sorted is the quick sort of everything that's smaller than the pivot. Okay, what is the quick sort of everything that was smaller than the pivot? Well, it itself is the result of merging together a smaller and a bigger. But we only want the first element of that. So that'll be the first element of this thing. And so that means that sort of at the outermost level, we have the first half of the list and the second half of the list. And we only want the first element of the first half. So we're going to recurse on the first half, and we're going to have the first quarter and the second quarter of the list. But we only want the first element of the list, so we only need to sort this. But this, we have the first eighth and the second eighth, and we just want the first element of the first eighth, so we only have to sort this. But that is the result of the first 16th. Okay, you can sort of get the pattern, right? So we're going to go down, we're going to divide the list in half every time until we basically get to the lowest level of recursion that quicksort would have gone to. And then we're just going to calculate that, and then we're going to sort of go back out. And so to me, I think the answer is that we only really it's sort of like we only really sort one element, but we sort of half sort everything else. By half sort, I mean, we know like we're partitioning it. So we partition everything into these bins that are sort of coarsely sorted, but then we're really only guaranteeing that one element is sorted. We found the minimum of the list. Now, of course, this is like a super inefficient way to calculate the minimum, but that's not the point. The point is that Haskell figures all that out for you automatically. So this seems like pretty awesome. I mean, the idea that the machine will always do, the language will always do the minimum amount of computation necessary in order to accomplish the goals of your code seems to me to be like awesome. Like, why would we ever not do that? Like, that seems fantastic. It seems fantastic that like we don't want to do calculations that we don't need. And so if our language can support us in just figuring automatically out what we need and what we don't need, and just like ignoring a bunch of stuff, it seems like it'll always be more efficient. Like Haskell code feels like ought to be more efficient than other kinds of code. And I think to a certain extent that's true. But there's some downsides. So like this seems like pretty awesome characteristic of a language to have. So what are the downsides? Well, one of the big downsides is it is virtually impossible to profile Haskell code. Okay, and you can kind of imagine why that is. It's because anytime you have a chunk of Haskell code and you have some expressions, and I mean profiling in the context of a real application, right? Not like unit test profiling. Profiling in the context of a real application, you have some chunk of code, and it might look like the code itself is very simple. Maybe just like something simple, like adds two numbers together, two parameters together. But if one of those parameters represents some crazy delayed calculation, and you try to go and like put some timing code around this little chunk, then the performance of the code does not depend on the code itself. It depends on the context that the code finds itself in. And context, and that's a dynamically changing context. In other words, sometimes I'll profile my little addition function and it'll give me one answer, and sometimes I'll profile it, it'll give me a different answer. It just depends on what has been deferred as far as evaluation goes. And so I was a little bit like, so profiling, like people who care about actual making code like reliable and deterministic and predictable, like hate Haskell. They can't handle it because you can't profile it. Sometimes things are long, sometimes things are short. It feels like you have no control over what's going on. And so I'd say pros and cons. Okay, so I just wanted to take you through that little thought experiment. Kind of cool that you get the minimum amount of computation necessary. Kind of annoying that deferred calculations means there's no such thing as profiling or performance optimization. Like it's super hard to reason about a Haskell program. I mean, to reason performance-wise about a Haskell program. Okay, so any questions or thoughts on that before we move on over to the rest of our lecture? Just thought you might like to see that. Great. Then let's go ahead and not this presentation, the other one. Haskell and monads. So what I'd like to do for the rest of our time today is start going through a little presentation I put together about a year ago, all about Haskell's type system. And so where we're headed on this is, well, I'll show you in just a second, but Haskell has this incredibly powerful type system and an incredibly powerful type inference engine, and as a result, can compile code to be very efficient. Haskell also has some pretty abstract type system stuff. Like we've talked about types, we'll talk a little bit about type classes today, but there's even more abstract things called kinds. So kinds is like one more thing that's even more abstract than types. So it's all this stuff that Haskell does, and it's actually very beautiful mathematically, but it is a little complicated. And so people like to make fun of Haskell, especially when you start throwing around words like monads. Everyone, like there's all these internet memes about monads and how like monads are so problematic, and like nobody understands what monads are and why they're even necessary. And so I decided I wanted to try to do a lecture all about Haskell. I mean, at this point, I think you've got the basic idea. Like we've seen the syntax, you've seen lots of syntax of lots of languages, there's some details, but really the last big interesting thing about Haskell is monads, and like, what is a monad? And why in the world do we need them? And all of those things. So the next lecture, and this will probably spill over till Wednesday, the point of this lecture is I really want to try to give you a sense of what a monad is. It's actually not that complicated in my opinion, but there are some interesting connections to other sorts of things that I'll try to take us through as gently as possible. Okay, so here's the problem. Let me show you the problem first of all. Problem is the following. So functional programming languages are really beautiful. You've got higher order functions, you've got anonymous functions, got these things called algebraic data types, which we've talked about. You've got all of this like immutable data structures, you know, because everything is a function, you can reason about programs really cleanly, like so awesome. Like functional programming, there's lots of real benefits to it. And we've even seen some other like sort of mathematical sorts of benefits. There's this close correspondence with mathematics. and you can do all sorts of like interesting equational reasoning with functional languages that you can't do with non-functional languages. You get things like Church-Rosser theorem. So like cool stuff. But the problem is side effects. So functional languages are beautiful, but they're not useful unless they have side effects. I mean, we've made this point before, but I'm just going to make it again. The whole point of running a program is to affect the world, and that means you need a side effect. Anytime you're doing input or output, anytime you're doing like interfacing to foreign languages, anytime you have concurrency, like all of these things can be considered side effects, and we need to be able to cope with all of them. And so for many decades, it was a real almost source of embarrassment to the functional language programming community that they had this amazing idea of functional programming, but that they couldn't manage it because like functional languages, you have to violate the functional nature of them in order to do anything useful. Okay. And I found this graph that I thought was kind of cool, that I think really lays out the kind of the issue. So let me pull up my little laser pointer here. So on the x-axis, you have how safe or dangerous is a language. And then on the y-axis, you have how useful or useless is the language. So for example, you can imagine a language that has no effects at all, a functional language, like a purely, like actually purely functional language. No effects. It's therefore totally safe to use because it's not going to do anything, but it is completely useless. You then have other languages like C. So a language like C is useful, like it's awesome. You can code whatever you want in C, and basically have arbitrary effects. And you can do things like function pointer arithmetic, and you can create function pointers to whatever you want. You can access memory anywhere you want, and you've got all this casting stuff that you can do, so you can totally circumvent the compiler's type checking system. And man, it's awesome, except that it's incredibly dangerous, and as a result, C programs break all the time, and like it's always feels like it's always C language programs that are the source of huge like bugs that cause all sorts of problems. Okay, so of course where we'd really like to be is Nirvana, which is a safe language that's useful. So there's sort of two ways you can get there. One way is to take a language like C that's dangerous but useful, try to keep it useful, and just move it to make it safer. So we try to move the language a little more to the right. So for example, in C++, maybe instead of using pointers, you try to use smart pointers. And smart pointers, you know, maybe that's going to help you with some of the inherent dangers of arbitrary pointers. That's like a safer version of C that's hopefully just as useful. Haskell, though, takes this plan. The idea is start with a language that is theoretically perfectly safe, and then try to start making it more and more useful. Okay, so this is what Haskell's trying to do. And oh yeah, I think we can skip this. So yeah, forget about this. Okay, so so Haskell is trying to take languages, it's trying to make them, it's trying to, for many years, it was like, well, we want to be this beautiful functional language, but we've got to be useful. How do we like reconcile this? And the simplest way to think about it is I/O. If you're going to have input and output in your programming language, you're going to have side effects. So how do we deal with I/O in a principled way in a strictly typed functional language? That's the key issue. And monads turned out to be an elegant solution to this problem. The idea being that by introducing this monad, you can, this thing called a monad into your language, that you could sort of get the best of both worlds. So you could have arbitrary effects, but you could essentially divide your program into two parts. There's like the affected part, like there's a part where there's effects, and there's a part where there's not effects. And so the part where there's not effects, the compiler can do all of its awesome functional stuff. And the part where there is effects, like the compiler knows that there's effects and has to be way more careful, but you can still like sequence things and reason about things cautiously. And then there's a principled way of interleaving these two parts of your program together. And monads are the thing that make that happen. Okay, so what is a monad? And the idea of a monad, I actually found this great blog post all about this that takes us through functors, applicatives, and monads. And so I'm going to try to take us through that same blog post. I've got lots of cute pictures, which I think are helpful for explaining the concept. Okay, so let's go. So we're just going to start building up some concepts here, line upon line, precept upon precept. So we're going to start with a bunch of little figures that look like this. Hopefully everyone can see these. Please just let me know if you can't. Okay, so we're going to start with values. And we all know that we can take values like this, and we can apply functions to those values, and we can get new values. Okay, great. So we're going to draw little pictures like this throughout the rest of this presentation. So values, we apply functions to those values, we get new values. Now, we also have seen things like the maybe type. And in the maybe type, remember that maybe of some type, you can be just one of those things or you can be nothing. So you can kind of think about this as a value. So so we could have just 2. It's like we've taken the 2 and we've wrapped it up in a little just box. So we're going to call the just part of this the context and the 2 part of this a value. Okay, with me so far? So we have a just 2. It's like 2 in a box. But what happens? Oh yeah, and so the maybe type, we have 2 things. We have just an A where A is some value. This is a variable here, so we put that A in the box, or we have nothing. So the context is like, you can have different contexts. Actually, we've seen this, haven't we? We saw the type constructor stuff. So we've seen type constructors, just a reminder. So you have something like maybe A is either nothing or it's just an A. So you can have like a value called country, which is just China. Or you can have a database thing, like a function from a database, look up age, which takes its first argument as a database, its second argument is a string, like maybe the username or something, and it returns maybe an integer if that person has an age associated with them in the database. Okay. So what happens if we try to apply a function like +3 to a value that's wrapped in a box? Well, the answer is like it can't. Like +3 doesn't know how to work on a just 2. +3 only knows how to work on the number 2. So this would give you a type error. Like it just doesn't work. So but there's this thing called fmap. Fmap is also called flat map. And what flat map is it's a function that knows how to deal with things that are wrapped up. So for example, if I call fmap, so fmap expects 2 values. It expects a function, and it expects a thing wrapped up in a context. And fmap knows how to unwrap this thing, apply the function, and then wrap it back up. Okay, so you can sort of imagine it like this. So you call fmap, you give it some function, you give it a value that's wrapped in a box, something mystical happens, and then, sorry, my laser pointer's getting my own way here. Okay, I've got to turn off my little participant and chat windows here. So if you need to, please feel free to raise your hand or something, but just note that I might not see it. Okay, so fmap takes these things, somehow magically it makes this thing work. Okay, so let's talk about this a little bit. So fmap is a special function, and a functor is any data type that knows how fmap ought to work on that data type. Okay? So I know this seems a little funny, but stick with me for a few minutes. So let me say that again. So a functor is a data type that sort of knows how to play nicely with fmap. So let's look at this little definition. So Haskell, like other languages, has classes and things like that. So the functor class is, you give me f here. F is a type, so it's not a variable. So this is like a class that's been parameterized with a type. And this is going to have to implement, it has to know how to implement fmap such that if you give me a function that maps A's to B's, and you give me a value A that's been wrapped up in type F, then it will return a wrapped up thing of type B. Okay, so for example, F might be just. So if F is just, then what that means is you give me a function that maps A's to B's and you give me a just A, then it will return a just B. So just is a functor if it knows how to do this. And in general, it's pretty easy to do this. And I can show you, I think later in this deck, I have some examples of how that works. Okay, so it looks like we have, oh, Taylor. Taylor says, it's helpful to think of classes in Haskell as interfaces in other languages. They define the type signature and the rules for other data types to implement. Yes, thank you. Thank you, Taylor, that's exactly right. So think of this as an interface. Okay, so hopefully everyone's with me so far. So a functor is a data type. So, so the idea is you need to be able to, like fmap needs to be able to, for if a particular data type is going to be a functor, then it needs to be able to implement this fmap thing. So it means we're going to have to basically take the wrapped up value, unwrap it, apply the function, and then rewrap the value in the new context. And so, and similarly, it needs to be able to, like if you give it things like nothing, then it would have to be not, like it'd have to know that if there's no value, then you don't apply the function and you end up with nothing. So I think, sorry, let me, darn. I thought I had some code here that showed how to implement this. I mean, this is really very straightforward. Okay, there's like, I'm using words like functor, but really, hopefully, you're just getting the idea. Like, it's like this isn't super complicated. Like, you can easily imagine 2 or 3 lines that would let us accomplish this in Haskell, right? I mean, we just like pattern match on just, and like we're done. Okay, so this is not hard, but we're just trying to build up a series of abstractions here. So functors are anything that know how fmap works on them. Okay, and let's skip this slide. Sorry, my little laser pointers keep getting. Okay, so here's the other thing. Let's think about what happens if you apply a function to a list of values. Well, you think of an array of values, you apply a function to it. What that means is you're going to take each value out of the corresponding bucket in the list, you're going to apply the function to it, you're going to get all these new values, and then you're going to wrap them back up into a new array. So it turns out that you can think of an array as a functor. So it knows how to do this. It knows how to play nice with fmap. Now, actually, let's skip this. Yeah, we're running a little low on time here. In fact, let me see here. Yeah, let's just keep going. So, okay, so that's a functor. So a functor is any data type that knows how to play nice with fmap. Now let's move to applicatives. So applicatives are just sort of like the next level up. So if a functor knows how to deal, is a data type that knows how to basically get unwrapped, an applicative is like, well, what happens if we actually took the function and wrapped it in a box? I mean, there's no reason that we couldn't do that. A function is this is a language that has first-class functions. Functions are objects just like any other object. And so we can easily take a function and wrap it in a context, just like we can a value. And so if you tried to apply a wrapped function to a value, you'd get an error. So an applicative is something that knows how to take a function that's wrapped in a box, take a value that's wrapped in a box, unwrap the function, unwrap the value, apply the function to the value, and wrap it all back up again. Okay, so it's just like the function version of a functor. So for example, just, you can think of as if we took just, and then this is a function plus 3, so that's wrapped up in a box. You all can see that. This is just plus 3, so that's wrapped up in a box, and we can use the applicative operator and apply it to just 2, and it will go ahead and unwrap this and apply it and rewrap it. So, for example, here is, we said that lists are functors, meaning that you can think of a list in the same way that you think of the just type. It knows how to play nice with fmap. And so that means but it's also an applicative. So what that means is it knows how to unwrap functions and values. So if we had a list of functions and a list of values, and we use the applicative operator, it will take each of these functions. So it'll unwrap the left. So, and to unwrap, remember, if we're unwrapping a list, what that means is we're going to sort of pop everything out of the little buckets inside of the list. And we're going to unwrap the stuff on the right, which means we're going to pop them out, and we're going to apply them, and then we're going to put them back into new buckets. So we'll take the times 2 function, pop it out. We'll take these 3 things, pop them out, apply it, and put them in. So we get 2, 4, and 6. And then we take the plus 3 function and these things, pop everything out, apply them, and then put them back in. Or in other words, you can think of this. This is what's happening. Okay, so we're taking these two lists and applying them in this way, and we're getting the final result. So an applicative is, like I said, it's something that knows how to unwrap a function from a context and then apply it. So I found this funny thing, this funny example. So if you took, so $ time, I should go back, sorry. Let's look at $ times really quickly. It maybe is actually useful to, sorry, let me just quickly scan. Okay, so less than $ greater than is the infix notation for fmap. Okay, so this expression right here and this expression right here are equivalent. Okay, so this is the pre-order version of it, and this is the infix version of it. Okay, so that's, I just wanted to point that out. Less than, $ greater than is the infix version of fmap. So now if we go back here, so if we take plus fmap just 5, then what we would get is the result of unpacking this thing and applying it to this, and then rewrapping it in a just. Well, this is a 2-argument function. And so by taking a 2-argument function and applying it to 1 argument, the result is a 1-argument function wrapped in a just, which is this. But if we tried to do this, it doesn't work. So because what fmap tries to do is it tries to take this value and unwrap it, so that gives us a 4, and apply it to this thing. But this is not a function, this is just a function, and so there's an error. So what you have to do is if you want to unwrap both sides of this, you need to use this applicative operator, and that will unwrap the left, unwrap the right, do the operation, and then wrap it back up. All right, I'm actually thinking that is a great place to stop. Wow, that went a lot faster than I thought it was going to. We only made it a little bit of like halfway through the lecture today, which is actually great. We'll just have a lot to talk about on Wednesday. So let's call it there. I'm sure you'll have questions. I'll try to make this as clear as I can. I think it's kind of fun to go through it. For now, though, I hope everybody has a great day, and we'll see you on Wednesday. Bye, everyone. And I'll stop recording now.